to the neighbors and has the neighbors protect themselves. The cell that is producing the interferon does not survive, it dies. So it sacrifices itself for the good of the multicellular organism. Makes sense? And then the last non-specific defense, it complements the rest of the immune response. We call it a complement cascade because the proteins, there's like 30 of them. And once you activate one, it's like pushing, those pennies, you're trying to push the pennies off. So if you push the one, or the quarters, all the quarters fall off in a cascade. That's kind of what happens with complement. You activate the first protein in the cascade, it breaks into two, and then it activates every single one of the other ones in unison and basically does not stop until they're all activated. So you can't turn this thing off, okay? The whole cascade happens. So what does it lead to and why do we care? When you activate the complement cascade, it actually, some of the proteins involved coat capsules. Where are we? Coat capsules. As they coat the capsules, then they enable the phagocyte to grab onto it. So it increases phagocytosis. We call that opsonization. Some complement proteins, when they become active, actually bind to foreign bacteria and blow holes in them and blow them up and directly kill them. So it leads to cell lysis. And then some complement proteins will activate the inflammatory response, which leads to inflammation, which then leads to more phagocytosis. So round and round we go with complement until all of the bacteria, protozoa, whatever it is that's activating this, that has activated the cascade, is going to be gone, killed. How do you activate complement? There are 3 different ways. The first one they discovered is called the classical pathway because that's the one they discovered first. The other pathway is called the alternative pathway. And the easiest one to remember is the lectin pathway. All right, well, what's happening? Interleukin 1 goes to the hypothalamus. Okay, we know that. Interleukin 1 also goes to the liver. It tells the liver to make mannose-binding lectins. Now, mannose is a big, weird sugar. Lectins that stick to the big, weird sugar. So we have this big, weird sugar. We have a lectin that was made in the liver. Once the lectin binds to the big, weird sugar, a binding spot opens up for other complement proteins, which will then start the complement cascade. So the lectin pathway uses lectins to activate the cascade. The alternative pathway, the one they found second, there are certain complement proteins, like I said, that will just stick to capsules. Once they stick to whatever it is they're supposed to stick to, a binding pocket will open up for the rest of the cascade proteins. The way I like to describe it is, I don't know, we played Tomb Raider years ago when the kids were little, and I'd sit and watch them play, and I would solve puzzles with them, and they'd press a button somewhere, and you'd hear it, you'd be like, oh my gosh, the door opened up, and you'd have to run through the door of the cave. That's exactly what happens here. Something binds in one spot, and it actually transmits a change in the bottom part of the protein, which opens up a trap door that allows other things to bind. And it's just like a lock and key. It has to fit like that. Now with my keys, you know how they all look the same sometimes, and then you don't know which one to put in the door? At least that's how I am. I can't look at the teeth. So I have to get keys that have all different things on them that are completely different. I'm like, oh, there's my house key. I know that has Yoda on it. Everything, I have no idea. Like the rest of this is how this is. Just those tiny little teeth. If you put the wrong key in the door and you try to turn it, what's going to happen? Nothing. So these proteins in the complement cascade, these antibodies, these T cells, all have very specific binding pockets, just like a key. And the minute that key fits into the right binding pocket, it actually turns, it changes something in the cell that allows these binding spots to open up. So we have a situation where the alternative uses a complement protein that activates the cascade. And then the classical pathway is the one they discovered first, involves antibodies, IgG and IgM. Okay, now antibodies, as you'll see in chapter 15, we'll see who makes them. The B cells actually make them. When the antibody sticks to whatever it's supposed to stick to in its binding arm, it has 2 binding arms per antibody, a binding pocket will open up. And that binding pocket could stick to complement. That binding pocket could stick to a phagocytic white blood cell. That binding pocket does a lot of things, okay? And that binding pocket, unfortunately, can stick to mast cells, depending on the antibody subtype.
What's it say under classical?
IgG and IgM. So these are specific antibodies, and the antibodies that activate the complement cascade are IgG and IgM. Now, where do those antibodies come from? As we were activating this, and as the phagocytosis was occurring, and you had this specialized antigen presenting cell, well, here's where B and T cells are involved. Like I said, you inherit these different clones. These clones of B cells, clones of T cells. You have a B cell that sticks to E. coli, you have a T cell that sticks to E. coli. The reason why they're called different things, the bone marrow, the B cells which are in the bone marrow, the T cells which are in the thymus. The B cells, their claim to fame is that little receptor gets secreted. The T cells, the whole cell is involved in whatever it is supposed to be doing. So, this antigen presenting cell pops out the foreign particle on its surface like a flag. If a T cell or a B cell is able to fit into that antigen, and we have specific ones designed for specific proteins from specific diseases. Why? Because we're alive, our parents were alive, and their parents were alive. My grandfather got diphtheria. He lived through it. Therefore, I'm pretty sure that I will have a response to diphtheria because my mom is alive and I'm alive. Now, in the next generations, with everyone getting vaccinations, is anyone going to be, have natural ability to fight any diseases? I don't know. That's one of those questions. That's the big question. Hopefully, we never have to answer that. But in the meantime, we want to activate the right stuff. We don't want to waste time and energy making antibodies to something that we don't need, like Ebola, for example, until we actually need it. So, this antigen presenting cell is holding up the antigen. A T cell comes along, a B cell comes along. Now, what kind of T cells do we have? We have T cells before they get activated. We call them CD. CD4, CD8, depends on the particular receptor. But what happens when they get activated, whether it's a B or a T cell, and they only get activated when they stick to what they're supposed to stick to, they get bigger and they divide into two. All B cells, all T cells, whenever they bind to what they're meant to bind to, that you inherited genetically, they get bigger and divide into two. One line is the memory. They make more and more and more of themselves. So I inherit one copy of this E. coli B cell, it gets bigger and divides, and now I have 1,000 of these